On our journey to understanding delta H, our next stop is to talk about something called the specific heat capacity. And the specific heat capacity, well, instead of 1 being defined as, since I've got a very nice definition for number 2, I want to talk for a minute about the units of specific heat capacity and its abbreviations. So, abbreviations. So, C sub S is going to be the specific heat capacity. Sometimes also called the specific heat of a substance, and sometimes called just the heat capacity, but we're going to go with specific heat capacity. And you'll see 2 sets of units for this, joules per gram degree Celsius, and you'll also see joules per gram Kelvin. And what I'd like to do is take a minute to talk about how these 2 sets of units are the same. So let me refer to the definition here. The specific heat capacity is the amount of heat energy required to raise the temperature of 1 gram of a substance 1 degree Celsius. Okay? And if we think about how would that definition relate to Kelvin, we know that 1 degree Celsius and 1 degree Kelvin, or 1 Kelvin, sorry, are the same size. So now let me see if I can put that on a slightly better footing here by asking the following questions. So if I were to take and try and get the boiling or the freezing point of water in degrees Celsius, it would be 0 degrees Celsius. And the freezing point of water in Kelvin would be 273.15 Kelvin. And then I take the boiling point of water, for degrees Celsius, it would be 100 degrees. And for Kelvin, it would be 373.15. And if we look at the difference between these 2 numbers, we will see that, these 2 numbers, that the difference between them is 100 degrees Celsius. It is also 100 Kelvin. So difference. 100 degrees Celsius, 100 Kelvin. That's because temperature changes in degrees Celsius and Kelvin are the same. Temperature changes in degrees Celsius and Kelvin are the same. And these will be temperature changes because in the definition, you are raising or changing the temperature by a certain amount of degrees Celsius or a certain amount of Kelvin. Okay? So keep that in mind. If you see these different units, you don't have to worry about conversions between them. Just make sure that you have your delta T, your changes in temperature, done correctly. Okay, so now typically we do talk all the time about the specific heat capacity in these sets of units, joules per gram degree Celsius. For example, some specific heat capacities that we will work with, the specific heat of water is 4.184 joules per gram degree Celsius. That means that it takes 4.184 joules to raise the temperature per 1 gram 1 degree Celsius. That's what it means. But for the next couple of slides, we're going to talk about something called the molar heat capacity. It is the amount of heat energy required to raise the temperature of 1 mole of a substance by 1 degree Celsius. And therefore, it has units of joules per mole degree Celsius. Okay. Anyway, so this one has the red star because that's what we use most of the time. And but let's talk about molar heat capacity for a few slides. So, and now let's also think about how do atoms and molecules absorb energy. And if we were to imagine a process where we start at 0 Kelvin and only talk about gases, at least initially, then atoms and molecules have no kinetic energy, but they do have potential energy. That potential energy is stored in their positions. And the potential energy comes from the attractions between electrons and protons. Potential energy also comes from bonds. However, to a good approximation, potential energy is constant. Electrons stay in their ground state. Bonds don't break. So each atom or molecule has constant potential energy. Not changing, that is, so we don't have to worry about it. It won't change, so it won't enter in what we're talking about here. Kinetic energy will change, that's what we're getting to. And then further, for gases, as we've said in our gases chapter, so there are no attractions, no potential energy between particles. No potential energy, and those are attractions between particles. So we don't have to worry about that either, right? Each particle, each atom, each molecule is alone in the universe, even though it collides with other particles. Okay. All right. But now let's talk about kinetic energy. We've talked about kinetic energy before. We have a proportionality between two things. We've said average kinetic energy is proportional to temperature. Okay. And as temperature increases, average kinetic energy increases, and average velocity of particles increases. And right, all this stuff is not new. Here's something that's a little new. Increasing the velocity of a particle is called increasing the translational kinetic energy and so we're just going to use that term, translational kinetic energy, and we're going to talk about different types of kinetic energy now. All right. Now, let's come back. So, monatomic, let's say just atoms. Atoms absorb all of the kinetic energy into translational kinetic energy. So atoms only have translational kinetic energy. And what that means to us is that, well, let's go to the next page and talk about what they don't have. So, diatomic substances can have translational kinetic energy, but they can also have other ways of taking in kinetic energy. They can rotate, and so for a diatomic substance, for example, you can imagine that if it rotates, a rotation uses kinetic energy. And therefore, whenever a diatomic molecule rotates, that's going to, and it could rotate this way, it could rotate, and the other way. There are multiple rotations that this can do. But that's not a translation. Translation is, all right, so translation is moving in one direction. It can be translating, but it can also rotate. And that rotation takes energy. So a rotation uses kinetic energy. And you might imagine that if there's a diatomic versus a triatomic, that a triatomic can rotate this way, it can rotate that way, it can rotate, right, all kinds of ways. And a triatomic has more rotations possible than a diatomic. Than diatomic. And a diatomic has rotations possible, but a monatomic or an atom has no rotations possible. Vibrations will be the same idea. So now, if you can imagine a diatomic, so a vibration would actually be, well, let's think of it this way. So you could have two atoms, and we've talked about vibrations in solids before. A rotation would be turning like this, where both of them maintain their position, but a vibration would be like this. And so I'm going to attempt to draw that. It's going to be, let me see, so something like a bond starting here, and then the bond, the two atoms move in one direction and then they move in the other direction. And so they're moving while in another way. That is my attempt to draw a vibration. And vibrations use kinetic energy. And so that's true for a diatomic, and for a triatomic there are more rotations for a triatomic. A triatomic. And so if you're going to talk about putting energy into materials, the thing that we get from this page is the more complicated the molecule, the more ways it has of using kinetic energy or taking in kinetic energy. So more complicated molecules, so note. More complicated molecules have more ways of taking in kinetic energy. Okay, it's just not about velocity or translation. There also can be rotations and vibrations. Now, let's look at some data for gases at room temperature. And what we're looking at is the specific heat capacity in joules per gram degree Celsius. And so this is a specific heat capacity. And again, this is what we're going to be typically working with. And this is a molar heat capacity. And the reason we bring this up at all, the reason we're discussing this, is because if you look at the molar heat capacities, you can see some trends that are not obvious any other way. Let me see if I can point them out if you haven't already seen them. For the substances helium, neon, and argon, if you look at their specific heat capacities, you'll see they're very different. But if you look at their molar heat capacities, they are essentially the same or very close to each other. And that's because each of these has So they're monatomic. And they only have translational. So the only way they can take in kinetic energy is through translational motion. And that leads to them all having the same or very similar molar heat capacities. So, and this is true of all monatomic substances. Monatomic substances take in kinetic energy through translation. And it's a little beyond the scope of this course, but it turns out that these numbers are exactly or very close to 5/2 times R, where R is the universal gas constant. And as we will see, whenever you're talking about R in terms of energy, R is 8.314 joules per mole Kelvin. And it's the same R that we use for the ideal gas law with different sets of units. When you're using the ideal gas law, R, the universal gas constant, has a value of 0.08206 liter atmospheres per mole Kelvin. That is only a different set of units. Now we have R, and we'll see R all over this chapter. Okay. Now, for diatomic substances, they too act similarly when looked at through the molar heat capacity. So diatomic substances have a specific set of rotations and translations that they can do. And so translations and certain rotations and vibrations. Okay, and all of their C sub S molar heat capacities are going to be 7/2 R. Again, because they can do specific things, they have specific ways in which they can take in kinetic energy. And as you get more complicated, you can start to see that the numbers are not quite as close as the monatomics. But down here, as things get more complicated, these are going to be 9/2 R or close to it. And you can start to see how molecules or atoms absorb energy on an atomic basis is related to how they are allowed to take in kinetic energy. Now, and you can see otherwise, without looking at the molar heat capacity, the numbers, well, more or less, can look more different anyway, and quite different sometimes. But we can get an understanding by looking at the specific set of units of what's happening on an atomic or molecular basis, which is really cool. And let's do one other case. Let's talk about metals. Metals all have about the same type of movements. They only have vibrations in place. Therefore, they all have about the same specific heat capacity on a molar basis. So, this is called the Doulong Pettit Law because they discovered this fact back in the 1800s, I believe. And but what's happening here is, so all metals are comprised of particles vibrating in place. And so there's no translations. There's only a prescribed set of vibrations. And it is again beyond the general scope of this course to talk about why, if there's only translations, how their specific heat capacities can be higher than some of the monatomic gases. They must have more ways, I mean, our short answer is they must have more ways of absorbing kinetic energy than the monatomic gases if this number is bigger. And beyond that, we start getting into quantum effects that are tough to understand. And, but I will mention that in addition to having vibrations of the atoms in place, not only in the X, the Y, and the Z direction, but you can also have vibrations along the series of atoms. So things are getting complicated, but what I love is that depending upon what kind of units you have here, something that looks more complex, we can start to talk about on an atomic or a molecular basis what's going on. And Einstein did some work on this as well, which is pretty cool.